Thank you, Paul, and good afternoon, everybody. It's a real shame I can't see you all, but I gather it's really well attended, the meeting, maybe about 230 people. So I hope you get some value out of this, and please do use the chat to ask questions, and we will try and follow up on all those. John has kind of set the scene, and I'm going to go into a slightly deeper dive into these topics. First thing first, PNT from GNSS, position, navigation and timing from global navigation satellite systems. It's very straightforward. You just track 4 satellites, and as long as you've got, you can make range measurements to each one of those satellites from your device, you can solve for 4 parameters, and those typically means your position, your easting, northing and height, or your X, Y and Z spatial coordinates, and you can solve for the offset of the clock in your device from some kind of system time. There you go, it's done. All straightforward, very easy. Only it's just not that simple in reality. And so the GNSS has moved on a lot, and it's now become a very, very sophisticated technology with lots of capabilities, but also various vulnerabilities. So if one thing, we now have 4 independent systems. There's GPS, the American system, GLONASS, the Russian system, Galileo, the European, and Beidou, which is the Chinese system. All of them have their own timescales. That means that if you solve for your receiver clock offset, effectively saying solving for time somehow, each system gives you a different version of that time. Each one of those systems also has a different spatial system. So if you're solving for your position from GLONASS, you get a slightly different position if you solve for that position using GPS. Now, there are ways around all these issues, but the point is they are different systems. But sitting on top of that are various space-based augmentation systems. So, for example, EGNOS, European Geostationary Navigation Overlay System, GNSS, the Indian system, WASP, the American system, QZSS is the Japanese system. And these offer additional layers of functionality and information to what these systems can do for you. Then there are various other forms of infrastructure developed often by private companies or sometimes by government agencies, which allow additional layers of information on top of that. So for example, AGPS is assisted GPS, which is run by commercial companies, and it enables you to get information to do with how the spacecraft are moving in space, the orbit of the satellites, and the behavior of their onboard clocks by a different method than getting information directly from the satellite. And that gives you additional capabilities. So GBAS, DGPS, RTK, PPP, real-time kinematic, precise point positioning are services and technologies that enable much higher levels of accuracy, but also additional forms of way of thinking about what you can do with the information. So to kind of put that in perspective, conventional GPS navigation solutions, that means the kind of thing your phone will give you a position at the few meter level, maybe to an accuracy of 10 meters. If you're using precise point positioning in the open oceans, you can get real-time positioning at the level of accuracy of about 10 centimeters horizontally. Real-time kinematic positioning will give you relative position between, say, a receiver that you have put over a known point and your own receiver at the level of a couple of centimeters in real time. So what you can do with these technologies has moved on considerably. Now, one of the really good things about all these systems is they were designed to be interoperable. So you can combine them. You can combine GPS, GLONASS, Galileo, and Beidou into a single receiver, single chipset, and you can exploit the systems in various ways. And that means we have a lot of choices. So the question is, given the context of the problem you want to solve, how would you design that system? What are the requirements? And what is the build going to be in the technology you want to develop? So let's look at it from another way now and talk about the things that can go wrong, because that will put our design of our system and the resilience we want to build into it in a certain context. And okay, the obvious the usual suspects, as we might say in a talk like this, would be things like space weather, for example. So, the atmosphere of the Earth, say above between 100 kilometers and say up to 1,000 kilometers, one way of thinking about that is to call that the ionosphere. And in that area of space, there are a lot of ionized particles, free electrons floating around. And depending on the coupling between the solar magnetic field and the terrestrial magnetic field, there's more or less energy in the ionosphere. Now, those variations in the ionosphere, first of all, they can distort the ranging that you measure to the spacecraft. And so when GPS was designed, this was a well-known problem. And so GPS was deliberately designed with more than one frequency of carrier wave available. So you combine the information of the ranging on 2 carrier waves such that you could eliminate the ionospheric effects. However, ionospheric scintillation is something different to the refraction effects, and scintillation will simply destroy the carrier waves completely, or wipe out those. So you actually can't get any ranging at all. And this can occur, in particular, close to the equator. There's a particular phenomenon known as the equatorial ionospheric anomaly, the EIA, and that causes significant scintillation. So if you're designing a system and you want to operate close to the equator, you need to be aware of the fact that that can take place. And that will be almost like a denial of service attack. It will periodically, it'll wipe out your signals from your satellite navigation system. Now, secondly, the signals are very weak. A GPS satellite typically transmits about 100 watts of energy, and a GPS satellite is about 20,000 kilometers away from the surface of the Earth. So the actual signals are incredibly weak. They're actually below the noise floor of L-band signals that you receive at the surface of the Earth. And it's only by use of clever code correlation techniques that you can actually make measurements at all. But that does mean that the signal, because it's so weak, it's very easy to either intentionally or unintentionally jam it. And some communication systems, for example, say for film crews, transmitting between, say, a boom, microphone boom, and a camera, will use L-band communication, and that will wipe out the GPS signal. Now, another obvious threat is really the actual lack of signal availability due to the environment within which you're operating, and I'll show an urban canyon in a minute. But then there are sort of more nefarious actors at play in the world who will carry out spoofing, which is a deliberate and malicious attack to, say, bring down a drone, for example, or to possibly carry out some form of terrorism. Now, another problem is the simplicity of the data processing algorithms. So, for example, there's a lot of sophisticated mathematics that can go into these things, but if your positioning engine is just simplistically using the code ranges to the GPS satellites in a very naive kind of way without any sophisticated modeling, then you get errors sitting on top. And that may or may not be important depending on what you're trying to do. And finally, we have this issue of what John referred to as DOP, dilution of precision. And that's really to do with the distribution of the satellites in the sky that you can see. Now, when we largely only had GPS operating, this was a real problem. So about 10 o'clock in the morning each day in the United Kingdom, there'd be a DOP spike, and your accuracy would degrade by something like a factor of 8. And so for just a few minutes, admittedly, it wasn't a long time, you would have a time when your positioning would be much more unreliable than it is normally. Now, that didn't matter 20 years ago when we weren't relying on these systems so much, but it is more important now, and we'll come on to that. But we can also think about this in a more serious and sort of system level type of concerns. And the first thing to do with clock failures, and even the failure of the system time itself. And we'll come on to that. I'll use that as a bit of a case study. But we also have the issue of what we call the system of systems. So now GNSS is a pervasive element of much of a country's infrastructure, and it might control, for example, the switching network in a power system. So if GNSS fails, the power system will fail, and that might mean that your GNSS device, which is connected to the power grid, then goes down, and then it has to recover when the power system comes back on. So we'll talk a little bit about what happens when a GPS receiver switches off, and when you want to turn it back on, and how quickly you can reacquire the positioning and timing capability. Now, because some of these systems now actually rely upon delivery of information via, say, the internet or via communications, then if there are national scale cyber attacks or denial of service attacks to various systems, that will also have an impact upon the overall architecture of the PNT integration into our national infrastructure. The next thing, okay, this sounds like science fiction, is something called a Carrington event. Now, I think it was 1858 was something like that was the last Carrington event. And a Carrington event occurs when you get a solar flare coming from the sun and it intersects with the Earth. Now, in the 19th century was one of these events, and the sky was as bright as day for I think for even as much as a couple of days. And every electrical device, certainly in London, there are records that all these things blew up and they caught fire. So if a Carrington event happened now, of course, it would fry all the satellites, at least on that side of the Earth, that were exposed to the solar flare as it moved past. Now, okay, so it does sound like science fiction, but we're just living through a global pandemic, and this has been at the scale of the impact, it's a 1 in 100-year event. So the probability of a Carrington-style event occurring in the next 20 years is roughly 1 in 10. Now, okay, so that's just a probabilistic argument, but it does mean that we can't afford to simply say, oh, well, that will never happen, because it could happen in our lifetime. And finally, you have issues around things like PNT terrorism and extortion and space warfare. You know, the fact is that somebody could just put a 10.23 megahertz beacon up on top of the Shard, for example, in London, and they could spray that out. You know, let's say they pump it out at a couple of hundred watts, and that's going to affect all of the autonomous vehicles and the taxis and the City of London timing system, because it would be a denial of service of the GPS signal. Finally, obviously, there's the current issue of space warfare, and let's not be naive about that. It may happen. So to drill a little more deeply into this, let's look at the situation of the urban canyon. So we said at the beginning, okay, you need 4 satellites to get a position fix and to calculate your time offset. But if you're in a deep urban canyon, you may only be able to see 1 satellite, and you may only see that intermittently. You may be able to see several satellites, but if you look down that urban canyon, you can see the only part of the sky you can see is effectively in a narrow arc above you, almost like a plane above you. And so your distribution of satellites is not even. You're not going to get satellites coming in from the side, and therefore your position fix is going to be affected by that uncertainty. On top of that, you can get what's called an NLOS, a non-line of sight signal. Now, often in big urban conurbations, you have these glassy and steel buildings, and they are excellent reflecting surfaces. So a satellite signal that you wouldn't be able to see can bounce off one of those surfaces and then be reflected. And so then the path length of the signal is then much longer than you'd be expecting it to do from the computation of knowing where the satellite is. How you'd utilize that information in a conventional positioning algorithm, your position would then get biased by the fact that you're not measuring the range directly to the spacecraft, but from a reflected signal. That kind of leads on to the general idea of multipath. And multipath is where you get these signals bouncing off. And let's contrast general multipath with non-line of sight. Non-line of sight is a very strong burst from a single satellite, and it gives you a biased solution. Generally, these signals splashing around off many reflecting surfaces causes what's called multipath, and that limits your ability to have an accurate position. And finally, we have problems of criminal activity in cities. And there was a test done recently in London to measure the frequency with which jamming signals were seen on a street in London. And over the course of a day, 4 vehicles moved past that were clearly actively trying to jam the GNSS signal in the vicinity of the vehicle at that time. So let me again going slightly more deeply into this, let's look at 2 classes of information that you need in positioning, and these are ephemeris and clock information. So in order to calculate your position, you need to measure ranges to these orbiting spacecraft, but you also need to know where the satellite was when it transmitted the signal that you used to measure the range. You also need to know something about the clock on board the spacecraft. Now, so this orbital information, we call that ephemeris. And the thing is, there are multiple forms of ephemeris information available, but it's the role of the control segment in a system run by, say, the US Air Force or run by the European Union Galileo. Part of the job of this control segment is to calculate the orbit of the satellite, predict it several hours in advance, and then provide the information about the trajectory of the satellite down to users. Now, depending on how well you do that, you're going to get better or worse positioning service. Now, if you aren't able to update that ephemeris information fairly frequently, then you get what's called an age of ephemeris issue. So whereby you're predicting further and further advance in time and with less and less accuracy. So when the Soviet Union collapsed and then Russia took over sort of running GLONASS, the system degraded considerably. So sometimes the orbits weren't updated, the orbit information wasn't updated for a number of days, and that meant that the information about where you thought the spacecraft was, based on the ephemeris, gradually degraded over time and got worse and worse and worse. But also, not all that ephemeris information is necessarily correct. So there's an organization called the IGS, the International GNSS Service. I serve on the governing board of that. It's kind of coordinated out of NASA Jet Propulsion Laboratory. And if you are interested in GNSS, I would refer you to the IGS. It's a very good source of information, like the RAN, but in particular, the IGS provides services of various kinds. And one of them that they provide is they basically compare the broadcast ephemeris as recorded by multiple receivers all the way around the world. And that made the IGS aware of the fact that different receivers can sometimes decode the orbital information in slightly erroneous ways. So that meant that not all of the orbital information that could be shared among users is actually consistent. Now, it's a fairly minor issue, but let's just bring it up as a possibility that you get this information down from the spacecraft saying how it's flying in space, but actually your device is decoding that incorrectly. But also, not all of these ephemerides are equal, so to speak, and that means they can have different qualities of accuracy. So the ephemeris that you can get directly from the orbiting spacecraft in this information called the navigation message, that might be good to the meter or sometimes down to the decimeter level of accuracy. But there are other sources of information. Other agencies calculate real-time orbits, and those real-time orbits are much more reliable and much more accurate. But also, not all ephemerides can be trusted. So in the spoofing process, a malevolent actor will try and upload information onto your receiver, which is just lies. It's saying the spacecraft are flying in a certain way, or it introduce like a new apparent signal from a spacecraft that is actually simply wrong. And when your processing engine in your device or your application tries to process that information, you know, trusting the information and using it as if it's all equal and fair, you just get wrong answers. And that aspect of spoofing is something that we do need to be able to protect against. So the second sort of case study element to emphasize an element of the system that's important are the clocks. So GNSS relies fundamentally upon clocks to measure ranges between your device and the orbiting spacecraft. Now, the clock that's sitting in the satellite is normally an atomic clock, and it's extremely accurate. The device that sits in the clock that sits on your own, say your phone, for example, is a very, very cheap clock, and that's why you have to solve for the clock offset to correct the poor quality of the timing information that's in your device. Now, But underpinning all that is the idea that any one system has its own so-called system time. And that means that you've got effectively a master clock that is defining what you mean by time for that system, say GPS time, for example. Now, the way in which a timescale like GPST is calculated is by using an ensemble of atomic clocks. Now, actually, we can do, to put this in practical terms, we can imagine it. So I want to imagine, I don't know if all of you have got watches, or you've probably all got phones at least. Let's imagine we want to construct, as a group, a timescale for ourselves. So, okay, obviously, so my little mechanical watch here won't do. So no one clock in our system can define time, because they're all obviously have their, this might break down, or it might run slowly, all those kind of things. So what we could do is we could all look at our clocks, and actually, for the sake of argument now, I suggest you look at your phone or your watch and say, what is the time now? And then we could all share the information about what our time devices are saying, and we can calculate the average of all those, and we'll call that our system time. So once we're then logging what our system time is any one time, and we can compare all of our timing devices to that system time, we can then characterize the offset and the drift and the rate of running of all our own individual clocks. And then we can publish those as saying, okay, if I want to try to gain access to system time, as long as I understand what the errors are in my timing device compared to the time scale, I can gain access to precise time. Now, that's a very prosaic and simplistic description of how a system timescale is developed, but it's really important to understand it, because maybe not the mathematics, but the fact that every system has to have its own timescale, and that timescale can fail. And a simple example would be, let's say we're all sharing our clock information, and then suddenly for some reason my watch goes a bit crazy. Okay, I've just by mistake I reset it, but I didn't notice that. And so when we fling that in to the time scale, suddenly the fact that my clock is no longer behaving as it was before will corrupt the time scale, and it will make it start to degrade and go wrong. Let's say my watch gets worse and worse and worse, but we don't notice that, and it's causing the time scale to start kind of misbehaving, we could say. But worse than that is the actual entire timing system can in fact fail completely, and that did happen recently with the Galileo system. Now, it's never happened with GPS, but you have had with GPS an on-orbit satellite clock just kind of going bananas, so to speak, and that did cause serious problems for both the ranging to that spacecraft and for the time scale until that thing was detected. Okay, so having set all that scene, I'll move on a bit more rapidly through the information I want to present. So as John pointed out, if you want to design a system, you tend to think about these 4 parameters: accuracy, continuity, availability, and integrity. So accuracy is just how close you are to the truth, right? To measure, almost a geometric measure of how well you're doing. Continuity is to do with the fact that you're going to carry out some kind of operations. Let's imagine, for example, you're landing a jet fighter onto an aircraft carrier. And so in the process of landing, you want to know that for the next few seconds, this thing is going to carry on giving you relative position to the carrier that you can rely upon to land the aircraft. Now, availability, I tend to think of that slightly more broadly than just percentage of time, but also how much of the Earth's surface that positioning system is available. Right? So, it's typically GNSS, for example, you can't use it deep inside a building. You can't use it underground with an underground train. You can't use it under the water. And then finally, integrity, and this is really one of the key ones for us in our discussion, is the ability of the system to let you know when it's failing, to let you know when it's degrading, and to give you some quantitative metric of the extent to which you can no longer trust that information. And many of our solutions to these problems that we're trying to address involve blending information from GNSS with other forms of sensors. And so the extent to which we are prepared to trust and weight the information from the different sensors is a critical part of developing a system. So, well, I won't belabor these points, but our current dependence on GNSS PNT, we see it in many, many places: logistics, navigation, supply chains, ambulances, financial time stamping, control of power grid synchronization. It's used in the aircraft industry to a great extent, and of course it's used in things like precision agriculture, and of course all the conventional positioning that ordinary people use on a day-to-day basis. However, what's coming perhaps should give us pause for thought. So one thing is we're going to need to grow food much more efficiently given the rate of population growth. And so things like precision agriculture play a role in making the usage of fertile land we have to make it more efficient. John has talked about connected autonomous vehicles and the issues of collision avoidance. We now have electric flying autonomous transport being developed in cities. So how are we going to make sure those things are able to land and fly and avoid smashing into each other? We're going to use drone delivery systems, things like organs and blood supplies, and for conventional delivery of things like Amazon goods, those kind of things. We have an upcoming problem with space traffic management. There are thousands of satellites being deployed in low Earth orbit, and we have to somehow manage the way in which they fly and keep them apart from each other. And GNSS will have a critical role in that. With 5G communications, the synchronization of communications involves both frequency and timing standards to make those to enable the 5G efficiencies. And so that is going to rely heavily upon GNSS for those timing devices. Perhaps it's of interest to government, of course, vehicle usage and taxation. There are big opportunities to tax people more fairly if you track the vehicles and use GNSS for that. But then there are big infrastructure developments around things like smart cities and smart intersections, in particular tests going in places like Hong Kong, where many applications are available at the street level enabled by GNSS. And then finally, if you want to increase the capacity of the rail network to carry more trains, then we need a next generation of signaling technology and awareness of where trains are on tracks. And again, the obvious choice to do that with GNSS. So many of these things are now becoming much higher levels of criticality in the infrastructure of the country. So it leads us on to this what's been called the system of systems concept, which is whereby position, navigation, and timing enabled by GNSS is pervasive and embedded. And so if one part of the system fails, it can lead to another part of the system failing, and then there'll be a domino effect. So a simple example might be that if your 5G network is being controlled by GNSS, and then there's GNSS failure of some kind, degradation of the system, then the communication starts to degrade. But if you're delivering information to try to augment GNSS through the communication systems, then the whole thing starts to creak and groan. But if you actually somehow took GNSS out completely, for example, things like a Carrington event or a system time failure, as indeed did happen with Galileo, then all of a sudden you've got a lot of vulnerabilities in a modern infrastructural system of a state. These things are intertwined, and we need some way of protecting against that. So let's talk about these three levels of definitions and requirements that we might consider. We're going to talk about, I mean, to a certain extent, these are sort of artificial boundaries, but it gives us a way of thinking about the problems of requirements definition. As John said, the idea of defining requirements is a vast and complicated subject, but you need to have some kind of way of unpicking it and a start point. So let's break it down into a user requirements, system requirements, and say element design. So by user, it means someone like me who wants to have a service using something like a phone, for example, or you might be dealing financial transactions and you want to have a system to discipline your atomic clock to make sure that you have a traceable form of information about when transactions are taking place. So that's the user. So the system design is then the actual overall architecture of that system. What sensors are you using? What form of communications? What is the nature of the hardware that you're using? Then break it down to the element design, are the individual components of that and what they're designed to do. So for a user, we've already talked about accuracy, continuity, availability, and integrity. Fair enough. Then you have issues for the user of the datum. What coordinate frame are you going to use to describe that information? And that can be different depending if it's a terrestrial application, a maritime application, an airborne one, or a spaceborne one. And let's at least put it in the context of a spaceborne application. If the various people monitoring the trajectories of their spacecraft in low Earth orbit don't all use the same coordinate frame, then how can they figure out if they're going to bang into each other or not? So, and of course, people will use different coordinate frames. So, for example, the Beidou system uses one system, GPS uses another, and so on. So we need to define what we're using. Then there's the issue of the timestamping that you use. So there are different timescales. The fundamental one is Universal Coordinate Time, UTC, and there's things like GPST, but they are different timescales, and they have different accuracies. There's a latency issue. How quickly do you get information at a certain level of accuracy? And then particularly for financial transactions, there are issues of traceability. Now, if you're a user, you might have an epoch rate. How quickly, how often, how frequently do you need this information? So as John said, if you're a ship out in the open ocean, maybe a position every half hour is okay. But if you're a collision avoidance system for vehicles moving at, say, sort of 40 miles per hour on a rural road, then you need an update rate much higher than that. And all these things will vary depending upon the application domain. So it might be a fender tracking, something put around the ankle to make sure somebody obeys a certain court order. It might be to do with space traffic management. It might be to do with container management. It might be a connected vehicle collision avoidance. All these different user domains have different sets of requirements. So whichever domain you're working in, you need to think specifically about what you're trying to do, what your vulnerabilities are, and how you're going to get around them. So at the system level, you might have considerations of mass, power, size, connectivity, integration of systems, the durability of it, what's its survivability, how quickly can it turn on? If the power fails, what's the battery life to carry it through? What is the integrity concept required? What kind of information must be delivered through the system to inform the user when the thing is degrading? How much of that information to do with integrity is handled at the algorithmic level inside the device itself, and what is reported then subsequently perhaps to a user? How many channels will this device have? Is it going to try and track 120 satellites, or is it going to track 5? All these have power and footprint considerations. And then finally, you have the choice of, do you want to track 4 systems? That's going to make the device much more complicated. Can you afford to just track 2? And finally, down to the individual hardware element of a system. It might be, for example, the design of the antenna. So, for example, with an antenna, if you have it open to multiple frequencies because you're using multiple systems which all have maybe slightly different frequency bands they're using, that means you have the opportunity to track more signals, but it also means you're exposing the antenna to additional noise sources. You have typically in a device like this a thing called an RF front end, a radio frequency front end, which is the part of the device that deals with acquiring and locking onto the signals. And that might have different search capabilities. It might try to track signals higher or lower levels of accuracy, and all these things have demands on the processor, which then have demands on the power and the rate at which the system is going to bleed energy from battery, for example. Then you might have the consideration of the clock that's in the device. Now, you might just have a very, very cheap $2 quartz oscillator, but you might want to have a chip scale atomic clock. In the last few years, almost atomic clock level of performance can be achieved in a much smaller footprint device, and that can help carry over of if you lose tracking on a number of satellites, then a chip scale atomic clock can act to help you maintain certain levels of performance. And finally, we have all the issues around the algorithms the code you use, the complexity of that code, and whether or not you're exploiting additional forms of information at the element level inside the system. So, as an example of that, let's just consider one example, and I'll talk more about these three things: hot start, warm start, and cold start. So let's imagine that your power has failed on your device, and now you want to turn it on again, and you want to as quickly as possible get back into the business of getting time, getting position from that. Now, in a hot start, what happens is that you already have all the information about the orbits of the satellites in the form of a broadcast ephemeris. So when you turn on the device, you can then reacquire your tracking, maybe at the level of a microsecond. It might you lose tracking to all the satellites. You have an existing broadcast ephemeris and clock information available on the device. You turn it back on again, and then you're locked back onto those signals at the level of a microsecond. So very, very responsive and very fast. Now, in a warm start, it might be that you have some crude information about where the satellites are flying, but you don't have information about the precise ephemeris. So that might take you a number of seconds to turn on. Now, finally, if your device has been off for a day, for example, or more, several days, and you bring it out of the cupboard, that's what we call a cold start. And when a cold start takes place, it might take you a number of minutes to actually start tracking satellites again. Now, all those classes of start can be augmented and corrected for if you're sourcing information to do with the orbits and the clocks in a smart way. And so AGPS, assisted GPS, is based on the concept that a user of a smartphone, for example, might not turn it on for a day or so, might turn off their GPS tracking, and then they turn it on again, and they want the thing to work quickly. And so in the AGPS concept, what happens is that the information about the orbits of the spacecraft and the behavior of their clocks is delivered to the device, to the phone, for example, via an internet service. So as long as the phone is connected to the internet, then it's continually updating that information about the orbits of the satellites. And that means the device can actually operate more efficiently, and you can effectively have a hot start without requiring to track satellites continually. I'll move on from the RF front end. If anybody's got any questions about that, we'll come to that. So, if that's the nature of setting requirements, what are the nature of the solutions, which will be dealt with much more in future seminar? But let me at least talk about some of the things that you can do, so that we aren't being particularly daunted. I mean, a lot of very, very smart people who've worked on these problems for many, many years. And the first thing, if you're unaware of it, is a thing called a Kalman filter. Now, a Kalman filter is a form of sort of mathematical algorithm which enables you to collect information from multiple sources and integrate it together, calculate what we call the state, which might mean your position and your velocity and your acceleration, but also critically, what you get out of a Kalman filter is the uncertainty in your position. So if you're able to integrate information, say, from GNSS and from an inertial measurement unit, for example, or from a Wi-Fi positioning system, the Kalman filter is a mathematical formalism that enables you to add together all that information and combine it. And that's where actually the weighting of the respective form of information can be effectively exploited to get an optimal position. Now, John talked about the idea of map matching. So that's the idea where you have a digital map base, and as you take your GNSS-derived position, and then you snap onto a vector, which is saying, I must be on a road because I'm using a vehicle navigation system inside a car, and then you're combining different forms of information. But as John pointed out, it's not necessarily perfect, and any errors in the underlying map base can, in fact, bias your position. Then we talked briefly about the idea of a chip-scale atomic clock, and obviously you can have things like accelerometers and gyros, cameras, and there are developments in quantum technologies which seem to be promising in a number of years very, very high quality accelerometers. One thing I should add as an element of caution and warning is that, of course, you can have an accelerometer, and an accelerometer, you integrate the accelerations, you measure, and you calculate changes of position and changes of velocity. But typically, unless the accelerometer is very, very expensive, it will tend to drift. And so typically, the way in which you control the drift of the accelerometer is by using things like GNSS. Now, that can be handled elegantly inside a Kalman filter. But if, for example, you have a very crude set of algorithms, an unsophisticated set of algorithms that might trust the accelerometer, it's not going to work very well. Then we have the concept of RAIN, Receiver Autonomous Integrity Monitoring. Now, we said at the beginning, you need 4 satellite signals to get a position fix and a clock offset. But what if you can measure ranges to 20 satellites? Then you actually have a choice of, do I use all those 20? Or should I actually just use 18 of them and then look at the other 2 signals and see, is there anything strange going on with them? So the fact that we now have multiple systems, GLONASS, Beidou, Galileo, and so on, and we have devices that can track many, many satellites, well, with many, many channels, it means we have ways of checking the integrity of those signals. And again, that's down to at the algorithm level. So the next bullet is advanced application specific algorithm design. So for example, if you're really concerned about clocks and timing, then you have options mathematically to exploit the information available to you to build in integrity. So finally, we have the idea of getting other forms of information. So as John said, for example, you might have just a camera that says, which way up is this thing? Is it daylight? Is it darkness? All those kind of things. So the idea of building resilience into these systems is obviously important, because if we look at what's coming, then we have to have ways of protecting various forms of application so that power grids don't fall over, autonomous vehicles don't smash into each other and people die, drones don't drop out of the sky, spacecraft in low Earth orbit don't start smashing into each other. And the good thing about, one of the things about being in the UK, of course, is we have a tremendous heritage both in industry and in academia in solving these kind of engineering problems. And the UK has a very strong space industry. So we have good opportunities to develop systems to deal with these coming problems. And as an example of that is the government's OneWeb purchase of this sort of nascent mega constellation that will consist of, say, 700-800 satellites operating in low Earth orbit and providing communication information and strong signals which can pick up information from GPS satellites or Galileo satellites from above, and then transmit some form of, say, integrity message or ways of combating spoofing. So there are many opportunities ahead of us. And, now we've had all that discussion, I would kind of bring you back to that slide that John put up, and just imagine, just imagine for yourself what you would do. You think of what your application is you've got in mind, and could I exploit these forms of inputs in some way to make this thing robust and resilient? So if I conclude, I'd say that really what matters here is ensuring that position, navigation, and timing is kind of resilient at the point of use. Now, that resilience can be designed in right from the beginning by considering our requirements of the system. So what kind of inputs, what processing algorithms, what hardware are we going to use, how these things integrate together, how is that information exploited and reported to the user? Does the device actually come up with a flashing red light saying, okay, stop now, or does it simply turn itself off so you can't use it? And a key part of that process is to understand all the vulnerabilities. And that might mean in the future, we need new system architectures and augmentation systems. But we do have opportunities to do that. So things like 5G, ubiquitous mobile communications, having things like low Earth orbit mega constellations may offer opportunities to solve those problems. Okay, that's my talk. Bang in on the minute. So I'll pass back to Paul and John to deal with questions. Thank you.